I didn't run the classes a day. I got a chair.
And how do you?
Yeah, it's about time.
I'm impressed.
How did you? How'd you find it? Did you just go through other IMSA students' friends and look?
Well, I knew that Ethan was your friend, so.
Did you find Micah?
I found the video of Alex. Oh my god.
Right now, like face.
Oh my god. I was so nervous.
Also, I for one appreciate the style choice today.
Oh yes, not changing out of my pajamas because I'm not dealing.
Wait, does that mean water's in the
I'm really house confident because I don't remember the last time I sucked.
How would you react?
I understand. Okay, so I will not take it personally because I know you don't actually hate me.
Okay.
Hey, fun fact. I don't hate you either. That would just so you know. Wait, you know that white? I mean, are you going to like get? You know they created.
I don't think so. I don't know if it's so cool. They're like really nice.
You build a dive tank underground and fill it entirely with water with a photon and because you are because your roommate last night. I saw that. I was up. Whoops. Catching photons. I saw that. So what is the photon's reference frame? What's happening? Wait a minute. I just realized something.
We have to record homework, don't we?
Yeah, let's check. Wait. How fast are we moving in the photon's reference frame?
In the what?
Oh, by the way, that's right. You want to look? Wouldn't we be moving the speed of light?
No.
Can't move the speed of light?
No. We would not be.
Oh god. That's the dog.
I know, it's a cute dog, right?
Wait, what?
My glasses fix themselves.
What?
Okay, here.
When the screen
You have a bus moving at a speed of light. These people, pets.
Everyone has done it anyway.
Actually,
I thought it was like
really good
I knew it was.
question.
You just, like, we were talking about it
Quiz
last
is
night.
Thursday, correct?
What's tomorrow?
Okay, I'm not gonna.
It's okay, you're fine.
Hey, that means we'll have.
I gotta finish with 4x4.
I'm going to
Okay,
jump
we're all
off
doing
the
bench study session for this
bridge
class today.
at relativistic speeds, of
I don't want to
course.
go to study sessions, Mike. I don't need to study. I mean, I don't need to
We
study.
study session today, all of us. When you want to.
No, I don't need to study anything. I don't need to do
Be
my
successful.
Hey, ready?
This class?
Number one, the top particle would.
I thought ad drop was in. I can still ad drop? You can't.
Oh, okay. Sorry. Wait, no.
I want to drop this. You can't do that. Because I need it.
So you should have, it looks to me like you should have, the top particle you should have E, and then root E squared minus 4, 0, 0, right? Oh, man. And the anti-tau should be 2, 0, 0, 0. 2 G. Okay. Number 2, the Z in the photon. The Z should be 90, 0, 0, 0. Photon should be E1, E1, 0, 0. Of course, lasons are always going to be 0, 0. That's a promise, more or less. All right, number 3, the answer is 2023 GeV.
2023.
Number 4, the charm port would be 1 GeV 0, 0, 0. The anti-charm would be 7,000 GeV root 7,000 squared minus whatever the mass of the charm port. What did I say the mass of the charm port? 1. Yeah, I guess it's close. Yeah, so it's root 7,000 squared minus 1 GeV, which, if you want an approximate form, is 6,099.99993. If that's helpful. And number 5, the answer is 32.79 GeV. Okay. Number 6, the answer is 44.74 GeV. Number 7, the answer is 45 GeV. Number 8, the answer is 45 GeV over C. I forgot overseas and some of the other ones. Okay. All right. So for number 9, one of the W bosons should be E, then root E squared minus 6400, and then the other one would be E and negative minus E squared minus 6400. The photon should be 6700, 6700. And the Z should be 90, 0. over 10 is 550.9 GeV. The challenge is root 501 over 2 root 2 GeV, or approximately 7.9 GeV. Yes.
It's not.
Oh, right. Yeah,
Are we gonna be in the egg pit again
I
today?
feel like it's 40 or 80.
Are you gonna bring a little poster?
And remember, it was a nice round number like that.
Yeah,
Yes.
a poster.
Why?
Sure.
It's like you gotta put your poster on the neck thingy that says your name.
Oh, is that a thing?
Yeah, like
Approximately 7.9. Number 9. The
envious
W4
Eden or
vectors
something
are
like that.
E,
Obviously,
and
Eden
then
the
root
edgy.
E squared minus
Obviously,
6400.
Eden the edgy.
The other one's the same, but E negative E squared minus 6400. Photon 6700, 6700.
Tumultuous
C is 980.
Oh my god.
Yes, I mean, there's no, I haven't defined a direction, so that's go over number 9. Read.
Which worksheet is this?
Sorry, I just can't do it.
Number 9?
I'm a little bothered by something I saw earlier, so it's also the answer my answer was off. Because, yeah. Well, so let's start with one.
I have not seen this option.
So, number 3, we have
Optimistic speeds out of a cannon.
the tau particle applies as an anti-tau and forms the Z boson. So, this is the tau. Alright, I'll just put it down. So this is that forms the Z boson, right? Doing something. Now, the sensible reference frame to use for the tau and the anti-tau is which frame? To use for the tau and anti-tau, which frame should we be looking at? The anti-tau is what? Well, it doesn't give you, it asks for the energy. The anti-tau's reference frame. Doesn't it ask for the energy of the anti-tau? It gives you the energy of the anti-tau. After the energy of the tau. No, it doesn't give you any energy. What do you mean? It says, it asks what's the energy of the tau particle, the anti-tau reference frame. Or it's number 3. Yes.
Oh yeah.
See, it's not just me. All right, so we're going to look at this in the anti-tau's reference frame. That's to say, it looks like this in the anti-tau's reference frame. The anti-tau's at rest. In this reference frame, the tau has this energy E. That's what the whole question's been asking about, right? What is that energy? It's a momentum that you can find using E squared minus P squared equals M squared, which you can basically always use, right? And you should use that one liberally, like, and with extreme prejudice. So, that gives you E squared minus 4 in this case, right? Because, so remember, if you have one of them, you can basically always find the other one in terms of the mass. And you usually have the mass. And even if you don't have the mass, you're probably trying to find the mass. So either way, you should have a variable for mass that you can use. Okay, good. Anti-tau is at rest. So its energy is equal to its mass, which is 2, and its momentum is 0. Okay, good. Now, the final state is the Z boson. And what would be a sensible reference frame to put the Z boson in? Its own reference frame, which is also the center mass reference frame, right? Where it is not doing anything, and thus the Z4 vector is just, what did I say, it was 90 or 91? 90. It's 90, 0, 0, 0. Okay, so that's the basic setup. At this point now, you can just say that T plus AT squared equals Z squared. We take the sum of the original particles 4 vectors, right, and set that equal to the final particles 4 vectors, and then square both sides. Say it again?
The zero line is in the anti-tau.
No. I get to choose, right? So, because there's the whole point of this is that these two things can be in 2 different reference frames. So I did an anti-top for this one. For Z, it's way easier in its own reference frame because then it's so easy to write the 4 vectors. So I just did it like that. That's huge. What did you say? It says to use inner products. This is an inner product. Right? Squaring it is really taking the inner product with itself. So when it says use inner products, that's what it means. Okay, good. So at this point, now remember you can expand this with binomial expansion. So t squared plus 2 t dot at plus at squared equals z squared. And the reason we do that is because the square of a 4 vector is equal to its mass squared, right? So the energy of a 4 vector squared is equal to its mass squared. Okay, good. So the mass of the child is 2. So this is, what's it say? That's 2 squared plus 2 times t dot at. So that gives you 2 times the energy minus 0 times that, so minus 0. Right? Product of the energy minus the product of the momentum. Okay? Plus at squared, that's another 2 squared. And z is 90 squared. Okay? Once you have this, you have this comes out to 4 plus 4, which is 8. 8 plus 4e equals 8100. Therefore, 4e equals 8002, and e equals 200. 0.5. Is that what you guys got? No, you got what I told you.
It's 8,000. It's 8,009.
Huh?
8,009.
Yes. That makes more sense. 8,092. And then you're dividing by 4, so that's 223. Oh, that is what I told you.
Yeah.
E. Oh, that's good. I was worried the answer might be wrong, but I saw something that I wasn't interested in, but it was just fine. Your question on that or something? Oh, great. Okay, so listen, the steps of this one. So this homework basically has, I forget, 5 or 6 of these problems on it, right? With a few of them giving you the steps of the 4 vectors. You need to be able to do it without the intermediate steps, right? I give the intermediate steps, telling you what 4 vectors to write as a bonus, a scaffold, as they call it. Okay, but on the quiz there will be no intermediate steps. We'll just ask the question, and you just have to answer it. So the way to do it, right? You figure out. You have a reference frame for the thing. There's always an interaction of some sort, right? And then you have the reference. One reference frame before it happens is the useful one. One reference frame afterwards is the useful one. You get to choose, but it's usually obvious from the problem. Then you write down the 4 vectors in the respective reference frame using an unknown quantity, right, which is the one you're looking for. And then you take the totals beforehand, the total afterwards, and you square both sides. And then once you square both sides, it's just done. Yeah.
Usually these events are the colors that happen.
It's hard to determine the right reference frame. If it's hard to determine the right reference frame, let's just say this. If you can write these things, right, it doesn't matter what reference frame you're in as long as you can write them correctly. So if it's hard to figure out which reference frame you should be using, you should try a few and see in which one you're able to write these properly. Okay? If you try the wrong reference frame, you shouldn't be able to finish it. And let's face it, the reference frame is basically always either one of the particles or the center of mass. So you don't have that many options. Right? You're not going to pick some random reference frame. Yeah. Sure. Okay. I shoot a proton. That energy 1,000 GeV stationary motion relative to the Earth. All right. So this one is proton hitting stationary proton in the Earth reference frame. Create a new particle, x, which is going to be moving in this way just by conservation momentum according to the Earth, right? All right, so in this example, right, as you have 2 things before you have, excuse me, 2 particles beforehand, 1 particle after. If we name these P1, P2, and X, you know the equation is going to look like this. P1 plus P2, that's the particles beforehand, and then X afterwards, and then if you square both sides, they'll be equal. Okay? From here, you can choose, now we have to fill in numbers for these, right? So P1, the Earth's reference frame is definitely the one that gives you all the information in the Earth's reference frame about the protons. It says in the Earth's reference frame, this thing's energy of 1,000, right? So 1,000 GeV. What's the momentum? Well, it's 1,000 squared minus 1, because the proton is mass of 1 GeV. And the other proton, the stationary one, is an energy of 1, its mass, right? Energy, because it's stationary, energy is equal to its mass, momentum is 0, 0, 0. These things, once you do a few problems, you realize they all fall into the same pattern, right? You're usually in one particle's reference frame that an energy equals its mass and the momentum is 0. Or you're given the energy and you calculate its momentum from E squared minus B squared equals M squared, right? That's not every single problem, but it's a lot of them. Yeah?
If like we're given a reference frame that's like say like in between, like is that like is there a
You have to be given enough information, and if you are, then you can do it. Yeah.
If the particles are phased into 2 different particles, then they have to move
In that particle's rest frame, yes. Now, if the particle that were in a frame where it was moving to begin with, they could both be going the same way. Right? But in the reference frame, the particle would have to be, right? What's kind of fun about this, I could, of course, write out the x4 vector. This x is that unknown particle it turns into, right? I could write out its 4 vector if I wanted to. I say if I wanted to because I actually don't have to. But if I did, which reference frame would I use for this? Center mass is by far the easiest, right? So I do this one in center mass because then it's not moving. And then it would just look like its mass, which I don't know, 0, 0, 0. The reason I didn't actually have to do that is because when it's the only particle that sort of happens anyway, this thing just turns into its mass squared. Right? So there's really nothing to do there. Okay, so if we take this, we expand it, P1 squared plus 2, P1 dot P2 plus P2 squared equals x squared. Then every time you have a 4 vector squared, you replace it with its mass squared. So this is the mass of the proton squared, which is 1, plus 2 times, now you have to do the inner product of these. So product of the energies is 1,000, minus product of the momentum is 0 mass. Plus, and then this is the mass of the proton squared, which is again 1. On this side, this will be the mass of the final particle, which is unknown, squared. Yeah?
Isn't it possible to do that one without?
Yeah. I mean, it's the same thing. You're actually doing exactly that by just taking the total E squared and B squared. I think in this case it ends up a little nicer still because you don't have to deal with this square root, it kind of drops away, but it would give the same answer. It's not that hard or anything. So on this side we have 2002 equals m squared, right? And therefore m equals, I don't think that reduces in any useful way, huh? And I would assume that that numerically comes out to the right thing. Okay, good. Yes.
I thought that when you have like the inner product of it would equal the mass. So
When I have the inner product of what?
like the P1 plus P2. So,
Okay, so P1 plus P2 is not a particle, right?
Yeah.
So when you take the inner product, you get this binomial expansion. These two are equal to the mass squared, right? This one is an extra term that comes from, it's a cross term for binomial expansion, right? So when you square a single 4 vector, you get the mass squared, right? But when you have a sum of 4 vectors, it's not actually the mass of an actual object. And remember, what was the name of this quantity? Varying mass. It's called a varying mass. It's not actually the mass of a particle, but it's sort of a hypothetical mass that could exist. Did that answer your question? Or did I yeah. Okay, good. So that's substituting in here the inner product of P1 and P2. So to do this step, this is the step where I need those 4 vectors I wrote down. It's actually the only part where I need to use these. Kind of nice. And so I look at the 4 vectors I wrote down, and inner product means product of the energies minus product of the momenta. So product of the energies is 1,000 times 1 minus product of the momenta is 0. Yeah. Photon, not proton. Very important difference. And that's very important. What's a photon?
Light.
It's a light particle. Photos. Photos means light, right? So photon is a light particle. I know we haven't gone through it in detail, but we can guess how fast they go. Okay, and knowing how fast they go, we can tell you what their mass is. What's the mass? 0 has to be, right? Once you know that the photon is 0, then you know from e squared minus p squared equals m squared, what can you say about its momentum? Equal to the energy, or plus or minus the energy, right? So the momentum of the photon is always plus or minus the energy. That's because it's massless. Because it's a massless energy momentum ratio.
Is it that every particle mass or just like
No.
which particle?
In the center mass reference frame, it is not generally true. The only time a particle's energy is equal to its mass is if the particle is stationary, right? When it's standing still, then energy is equal to mass. So we choose center mass reference frame when there's just one particle, because then it's standing still and its energy is equal to mass. Otherwise, if you do center mass on this one, that will not be true for either of them, and you'll not get anywhere. Does that make sense? Matt?
Can you go over them a second?
Sure. Okay. The Z boson decays later to form 1 electron and 1 positron. Remember sets, that's all you need to focus on. This one is kind of a compound problem, right? But the Z boson decays to form an electron and a positron. Oh, you don't know the things, fine, let's call it E and E right now.
These are
So, we will learn all the particles later after the relativity unit.
That's exciting.
So, good. Well, yeah. So you want to know the energy, it says, of the electron in the Z's reference frame. This one you don't have to do the 4 vectors, but you could, right? I can show you that. It says in the Z's reference frame, that means you have a stationary Z that goes to an electron and a positron. Okay? The stationary Z's energy, therefore, would be equal to its mass, which is 90? Did they say 90? Okay. So, right, it would be equal to its mass because it's in its own reference frame. Now, it splits up into the energy, the electron and the proton. What do you know about the electron and the proton's mass? They're both massless, right? So, because they're both massless, and because this is, the total momentum of this is going to be 0, right? Therefore, these two momenta have to be equal and opposite, right? So they both have 0 mass, they both have the same momentum, that also means they're going to have the same energy. And therefore, that has to split into 45 and 45, and then the momenta will be negative 45 and positive 45. Yeah.
So is that like a general rule when you have one particle split into like 2 identical particles, you can just like divide by 2?
Yes. If one particle in its own reference frame, right, only in its own reference frame, if one particle splits, a stationary particle splits into 2 identical particles, the energy has to divide by 2. Now, if the particle is moving to begin with, no good. If the 2 particles are not identical, also no good. Right? It's a special case, but that case comes up from time to time. Just for fun, you can do this with a 4-vector approach, right? I asked what's the energy in the Z's reference frame, and so you could be like, okay, electron has an unknown energy E in the Z's reference frame, but its momentum has to be equal to its energy, right? The momentum and the energy has to be the same because it's massless. The electron's not actually massless, but its mass is so small compared to everything else that you can treat it safely as massless. It works fine. We do that all the time. The positron.
Oh boy. Smash him again.
You could say, well, I know it has to have equal and opposite momentum because I know the total momentum is 0. Right, so I can do that trick. And I know that the energy has to be equal to its momentum, except that energy, of course, has to be positive. Okay? And once I do that, I could do z squared equals e plus p squared. If I do that, I would get z squared equals e squared plus 2e dot p plus p squared. And then you get the mass is e, so 9e squared equals e squared plus 2 times e dot p, and that would be e times e, so e squared, minus e times e, which is negative e squared. There's a minus sign, so it becomes plus e squared plus e squared. And that gives you that 90 squared, or let's just do that 8100, is equal to 4e squared. And then that means e squared equals 8100 over 4, and that means that e equals 90 over 2, which is 45. It gives the same answer. If you like this way better, okay, which honestly I do, I admit to this test, but I am actually more comfortable with the kind of regularity and predictability of this way. So if you feel that way, then go ahead and do it this way, even if it seems like there's another way to do it. You can do it that way. You can use them both as cross checks on each other. No?
How do you use e squared?
Sorry about the this
On
line?
the second line, we have
This line?
e squared at the beginning, right after the equal sign. How
This?
is that equal to?
Okay,
When you do the dot product, it's e.
Yes.
E squared.
yes, wait, hang on. Yes, and you're right, and I did it all wrong, thank you. Okay, this is the mass squared, which is 0, right? The electron product mass massless. And now this answer actually works, I'm sorry. Thank you for catching that. No one else noticed that I completely did it.
Well, I'm trying to figure out how that added up.
Yeah, that was my
You
confusion.
should point it out to me when I do that. Dr. Dog.
When I pointed it out, I wanted to make sure I was right.
That's true. That's fine. Well, thank you for pointing it out. Dr. Dog is frequently incorrect, except that he's not. And, yeah. Dr. Dog makes algebra mistakes a lot. Okay, good. That was good. Are there more questions? So the point is, there are a lot of questions where you can use this approach even though you don't need it. Like basically the whole homework 9, you could use this approach, and and it would be fine. It would work. It would be a little bit slower, but if you're good at this, that's not that bad. So if you want practice with this technique, this 4-vector approach, you could go back and do all the homework 9 with it, right? It won't hurt, right? It's not necessarily the best way of doing every problem, but it will give you some practice and you already have the answers to compare to. So it's a thought. Yes, sir?
We'll still need to remember like that e equals e squared over square root somewhere in
The definition of energy? Yes. Yes, you'll need, but take out the C's, you don't need it anymore. But yeah, the definition of energy momentum, you still need this. Yes. You may have to do Lorentz transformation with energy momentum, although you always have a way around it. Sometimes it's easier to do it. If you have enough information, it can be easier to just do it directly. You will not be asked about the space-time Lorentz transformations or velocity transformations. You will not need to know any of this. Yes.
Also, for the Lorentz transformations, is the gamma the velocity of the light?
Yes. Gamma is still based on velocity of the reference. Always. Okay. Good. Any other questions? All right. So what I want to do now is let's have some fun.
Oh no.
Fun to you or fun to us?
Is there
there a difference?
This is not preparation
In your reference
for.
frame or not?
This is not preparation for bar quiz. Okay. We have covered the preparation for bar quiz. I have nothing else to prepare you with. I've given you every resource I have. It's not. Oh, by the way, I was off. The 4 vector stuff is in chapter 4 of the book. By the way, chapter 3 is Introduction to Energy Momentum. Chapter 4 is the 4 vector stuff. So you're welcome to find out stuff in there. Yeah.
Where do we go tomorrow?
Oh, yeah, thanks. What day is this? What day was the quiz last time? Was it Tuesday? Thursday last time? The Tuesday before that?
Yes.
Okay, so that place. So as I can, I guess.
Okay.
Best place I could find at the moment. So yeah, as I can tomorrow. Thank you for the reminder. Everyone's here. Yeah. So as I can tomorrow, and we'll go from there. Good. Good. Okay. Yeah, okay. So, like I said, yeah, this everything, I've given you all the resources I have for this stuff, right? The rest is just practice, be ready for it. I'll give you problems of the type of homework 8, homework 9, and homework 10. Right? Yes?
Like, will there be anything that
All in one dimension. Yes, Edith.
Are the videos on Moodle yet?
Say it again?
Are the videos up on Moodle yet?
The improved videos are not up. ITMC will take some time, but you can run it yourself if you're desperate with VLC Media Player.
Okay.
It may be installed on your computer already. If not, it's free.
Okay.
VLC. And VLC basically will play anything. It keeps all these really old formats that most things don't.
Is this your stuff?
So VLC still works. I tested it in other students that it works still. They will get upgraded to, sadly not in time for this, looks like, but probably in time for the exam. I just saw Bill and Kevin today, they told me that they need another week. They're really busy right now. Any other questions over there? Yeah. Okay, so this is not for preparation for tomorrow's quiz, but it is A, something fun to think about, and B, preparation for the exam. Which is not that soon, by the way. It's October like 4th or something, 6th, something like that. Anyways, it's not that soon, but I mean, it exists. So there's a type of problem I'd love to ask. And this is one example. This is the most famous example of it. If anyone's seen this one before, then kindly keep your mouth shut, because like I said, as with many relativity problems, the learning happens in trying to figure out, not in getting the answer. Okay? If you just blurt out the answer, then no one learns anything at your table. No fun. Okay? But if you people say things and you say this is why that one's wrong, this is why that one's wrong, and how would that be? It enriches your understanding of relativity. This one for me made a big difference in my understanding of relativity. Here we go. There's a train. Proper length L.
Is it crystal clear?
Sure.
Yeah.
Here is a tunnel. Could be a crystal tunnel too if you want.
Crystal.
Proper length of an L. So the train and the tunnel are exactly the same length.
The heck?
Yeah, right? Exactly. Okay. Up here is a bomb.
Of course, it always is.
No.
Always a bomb in a train, right? The bomb blows up when it reaches the front of the tunnel here. Like I said, if you see it, if you think you have the answer, hold off a little bit, right, so that you can make sure everyone has time. Because every now and then someone can see it right away. Yeah.
How far away is the train from the distance?
Oh, I haven't shown you what it's doing yet.
Okay.
Yes, ma'am.
the train go through the back of the tunnel and then it's
So the train's going to go this way, right? The train's going to go through the tunnel this way.
from the back and then it hits the
In like this, right?
Okay.
Yeah. Okay. Over here is a sensor, and it deactivates the bomb.
Oh, that's evil.
Here. Okay, now classically this is actually very uninteresting. Both things happen at the same time and it has to do with, I don't know, the firing mechanism of the bomb. But relativistically it's much more interesting. Because now let's say the train's going through the tunnel, as you might have guessed it's going to happen, right? So now let's look in the tunnel's reference frame. It's stationary, it has a length L. The train in the tunnel's reference frame will have a length L altogether, less than L, right? So you will have a contracted train, let's just exaggerate it, a contracted train going through the tunnel. Okay, if it's contracted, it's shorter than the tunnel. Therefore, it reaches this point. Sorry, it got a bit bigger for some reason. It reaches this point before it reaches the end of the tunnel, right?
Yeah.
So what happens? The sensor is triggered here, right? And therefore the bomb is deactivated. Now, let's consider now the train's reference frame.
Don't do this.
No, make it stop. The train's reference frame. The train is length L. What is the tunnel doing?
It's getting slow.
It's
It's very slowly.
The tunnel is moving over the train, right? The train station is all moving around it, right? So here's the tunnel moving over the train. But what's the tunnel look like? It's shorter, right? So now the tunnel's moving over the train. The tunnel's moving over the train. Then this end hits this side first. And what happens?
Bomb
The
explodes.
bomb explodes. So this says no explosion. And this one says explosion.
What about from an observer's reference frame?
Well, that's really
Don't add to it.
But hang on, that doesn't matter because here's the thing. Two different reference frames. But the bomb has to either explode or not. Now hang on a second. The bomb has to either explode or not. Right? That has to be something that is agreed on by every reference frame. Because it's an explosion. You can't miss it. It's not a relative thing. Death is not relative. So, because of that, yes, I know, words solidify. So because of that, see, we found something that's the same in every reference frame.
Pain and suffering.
I thought math was true in every reference frame.
So yeah, so I have two things. Death is apparently an inner product of none.
That is the inner.
Okay, so the question is clearly that these cannot both be right explanations. This is not an answer that can be relative. So the question is, does the bomb go off or not? And of course, why? So what I want you to do right now is talk to. So this is not about energy momentum, right? This is all around simple stuff you know. So go ahead and talk to each other and see what you think.
So I've already heard
It's not required to
be quiet for the next 10 minutes.
I'm gonna say I'm pretty sure the bomb doesn't go off. If I had to guess, I would say the bomb doesn't go off. And my reasoning is in the Earth's reference frame where
That's the reason why I asked you to the observer. I'm like, if you're in the Earth reference
if you're in the Earth's reference frame, it doesn't go off. And so I'd say that has to be true.
In the Earth reference frame, don't when both things happen at the same time.
Wait, hold on a second. I just have to ask if I'm on the right track. Does this go into Schrodinger stuff?
Actually,
The bomb is both detonated and not detonated?
No.
Okay.
At the end of the day, something has to
Until you
happen.
observe it, the bomb is both detonated and not detonated, is it that?
I love it. Oh, don't go into that. No, we
Schrodinger's cat is a good cat.
Okay, but...
No, he both is and is not a good cat.
He's both. Schrodinger's cat is both nice and not nice.
Yeah, he's nice and mean at the same time, depending on your
He's not your dog.
The episode of Rick and Morty where they're unsure.
Exactly. That's what I was referencing.
You know that it ended up literally trying to run the animation of all 64 different worlds crashed to the animators' computers.
Oh my gosh, that's beautiful.
And they had to start over on it.
That is wonderful.
How long do you think it doing like that?
Are you going to ask if this is not the cat?
I'm gonna ask if it's
So in the trees are about half a second. Trees reference frames. Lasted like 3 seconds.
So, is the answer that until you observe it, the bomb is both detonated and not detonated? Okay.
Next unit, that's too soon. No.
Move that like that.
by the way,
Pick it up there.
you'll observe it if it blows up.
By the way, how fast
That's true.
What did you say?
How fast is the train moving?
How fast is the train moving?
Is it moving at normal speed or relative speed?
Doesn't matter, right?
Even if it's
to work, no matter how fast it's moving.
Even if it's moving
so if
at
it's got
normal speed, it's still like
yeah, if if it's going 60 miles an hour or if it's going, you know, a gamma of 35, right? It still needs to work either way. Yeah.
There's no solution to this. It's not.
I guess if this one doesn't have to be, but that would be a weird tunnel.
Yeah. Okay, here.
I mean, you really only need the tunnel.
I really feel like the answer has to be that the bomb doesn't, detonate, but I don't know how that's even
I
possible.
feel like the trigger for the thing to make it so that the bomb is inactive would make it take like
Wait. Yeah. Okay. Events that are simultaneous can only be simultaneous in one reference frame. So in the Earth's reference frame, it's simultaneous that it reaches both ends, meaning that it will never reach both ends in any other reference frame, which means that any other reference frame.
Cookie cutter problem.
In any other reference frame.
No, I think we were supposed to already realize that and still come up with something.
I know, but we're saying it's like the cookie cutter.
Yeah.
In the sense that even though it seems like it should be impossible for, you know, the bomb to not go off, the bomb has to not go off.
Yes.
But the same events must have. So there's two different events. That's what we're measuring now.
Yeah.
It's two different times.
How do you know, Micah?
Because it must be. That's how it must be.
That doesn't make a difference, Micah.
So the bomb doesn't go off.
What?
The bomb doesn't go off?
It depends on which one it is.
Which reference frame?
No, it can't depend. No. Think about it.
You're right.
Events can't happen in one reference frame and not happen in another. That's not
They both
possible.
happen. That's what it is. They both happen.
No, it's not. They can't both happen.
Why not?
Why not?
It's only a 50-50 problem.
They can't both go
Wait,
off
why
and
not?
not go off. What do you mean?
Because so in one event it hits here, right? In the other event it hits here.
I do not know.
Yes. So if we're treating reaching the sensors as events. Are we treating reaching the sensors as events?
Yes, we're treating each of them as events in their own separate.
In some way, though in a veiled way, this is the same problem as the cookie cutter.
Yeah, we got that out long ago.
The way in which it is not super obvious. So, maybe.
Alright, so here's the thing. Are you attempting to say that the bomb goes off in some reference frames and doesn't in others? That's not possible.
Wait, is this the thing where it's like it moves differently?
Like the cookie cutter problem, it happened at different times.
Explain.
Are we just
I
wait?
thought the cookie cutter problem just involved diagonal motion.
Well, it did involve diagonal motion, but it also involved, because you have the two types of ovals. You have the one oval here, and then you have the other oval, which is weird, because it's like... No, never mind.
Yeah, you're not making any sense.
Never mind. I just corrected myself.
Do you actually know, or you just don't want to talk?
He doesn't actually know.
I do know.
Benji, do you?
Yeah.
Do you know? Okay, so
Spill.
you said diagonal motion was the angle, but there is no diagonal motion.
It can't be diagonal motion here, that's true. So here's what we have to think about. In the cookie cutter problem, because we know that the cookie has to be cut in one reference frame, we know that it ends up, because I actually think a better way to look at this is the ruler of the...
Does this have to do with the tunnel compared to the train?
okay. I think a better way to look at this is like the problem on the quiz where the ruler is moving along and it has to fit through the hole.
Yes.
I think that's a good way to look at this. So when you think about it, you have it fits through the hole in one reference frame, so it has to fit through the hole in every reference frame. It's the same with this. It fits. Oh wait, no. I don't know where I'm going with this.
I don't think that works like that, but that was a good thought.
Yeah. Okay. This doesn't make it. I don't understand.
Train can be
Okay, so actually, let's go back to your paper thing. So the paper falls down, right, and you're going through this at light speed.
Yeah.
Okay.
So none of that requires
Now,
a
from the
physical
paper's
barrier
reference
that
frame,
changes things. So that would
this
be
is
enough to do.
tunnel.
I don't actually. I don't
Right.
know.
Is there another piece of information that we're supposed to be able to derive from the information
No.
we have?
This is purely theoretical. There's no math information. This is purely theoretical.
Well, that is what the train sees. Right? The train's reference.
I love
But I
theoretical.
mean, that's the point. They're equivalent.
I like theoretical physics when it has to do with general relativity instead of
Math.
instead of this, yes.
Special relativity.
Okay, hit number 2. As with all of these so-called paradox problems, everything I told you here is completely accurate. I didn't make any mistakes, but I made one hidden incorrect assumption somewhere.
Oh, okay.
Let's put it this way. As with the cookie cutter problem, it's about simultaneity. But the real simultaneity is so it looks like there's 2 events going on here, right? Bomb blows up, sensor deactivates bomb. Actually, there's 3 events. And the simultaneity has to do with the 3rd event, which I never mentioned. There's a required 3rd event somewhere in here that you're assuming is there, and that's what the simultaneity problem comes in. See if you can figure it out.
I thought I knew the answer. I was wrong.
Of course you would.
Well, I just figured out the right answer. I was going to tell you, but now I won't.
Oh god, this is pages long.
Really? Actually, I think
Oh no! Just find the answer, Eden.
I'm trying. Look, the solution is 4 pages long. Okay, Micah?
Just go down to the conclusion. Okay, so
no, it can't be entering it because then exiting would be an event too.
wait.
It doesn't exit though, because if it exits, the bomb goes off. So if it exits, we can proceed that the bomb can go off.
The conclusion is that no material object is perfectly rigid. The train must compress.
Oh.
What do you say?
Okay, so the train. It must be the. So in other words,
if you look
the
it up,
bomb
it's gonna
doesn't go off.
spoil it.
Yeah, don't look it up.
But
Okay, I'll just look it up
You
on
just
my
looked
own.
it up.
this one.
I'll look
So
it up on
how
my
does
own.
that fix that?
Don't do it.
Because the train goes smaller.
I already did.
How dare
Very easily. I am sorry. I like to know about things. I am too curious and impatient.
Front end intro, back end intro.
No, that's not an event. Neither one of those are events.
What do you mean?
The front end and back end, there's only one extra event.
What if there's just at least 3 events?
I lied. I couldn't find the answer. It's all just questions, and then it's like, oh, this has been left as an exercise to the reader, and I'm like,
I really can't figure out what the 3rd event's supposed to be. What are things we're assuming happen?
We're assuming the bomb blows up when it reaches the right end.
Oh wait, but no, it does. So we know that the bomb goes off. Here's the thing, he made an assumption.
Are we assuming the train enters the tunnel?
Micah?
What about rotation? No, we're not.
What?
Actually, Micah,
I'm
that
sorry.
was my theory. That was
Yes.
What?
I asked if it was the curve, and it wasn't the curve.
No, I was talking about say. Never mind.
Exactly. I'm smarter than you, Micah. I know what you're talking about. Just saying it to be arrogant.
You sound like an incel.
I sound like a what?
Then you
I
both
got
say it at the same time.
See, Benji, you may be smarter than me, but at least I have friends.
What is your guys' problem?
I apologize.
Can we just agree that we're all losers?
I agree.
I don't think Dr. Dog's loser.
Okay, except Dr. Dog. Obviously not Dr. Dog.
Is like the
That goes without
universe. It can't be
saying.
the loser.
Dog is the center of mass. Dr. Dog, according to my planetary science class, Dr. Dog's head
Is the only correct
Just according to logic.
what? No, it legitimately is possible. It's head
Oh, because it is like the best thing to do is
Think about that.
And your reference, right? Okay, wait. I have a theory. Oh God. I think that one of the I think the other event is we're assuming that when the sensor triggers that it then happens immediately. That here's the thing: the sensors are on opposite ends of the tunnel. The triggering of the sensor has to get from one end of the tunnel to the other, and that that can't happen immediately.
No, how fast can it go?
It can only go the speed of light.
Right. Okay, good.
Okay.
You guys can figure out from everything.
Oh, well, in that case.
Oh my god, I said that earlier and I thought it was dumb.
Oh.
Wow, do I have a bit better handle on physics than I think I do?
Yes.
Whoa.
So, I think the events have to be the triggering of the sensor, the arrival of the information at one sensor, and the detonation of the bomb. So, in the reference frame where the length of the train contracts,
Okay, say the train's moving at like 0.9 km.
yeah, here's the thing. In the reference frame where the tunnel contracts, the train is still, it's already going to be out of the tunnel before the information reaches.
Well, the information can be going at the speed of light, so how fast would it have to go to catch up to the other one?
We're just going to be walking around the whole class.
I think we can just assume it.
Actually, wait, yeah, I think the bomb has to go off in all the reference frames because, the bomb goes off in all the reference frames. Because information can't transfer. No, it can't. No, it can't.
The third event that I did from you, that several of you figured out, and some of you figured out early, and I deliberately tried to leave you away from it just to see if you figured out.
Information can't travel at the speed of light.
Because
I did that, last year. Manny got it in like a second. He had like the right answer. And I said something to lead him away from it, and he got confused with the whole rest of the class.
Yes.
Right? Yeah. That's exactly what always happens, right? Okay, so the hidden third event is that the sensor deactivating the bomb is actually two events because it has to happen in two different locations because the sensor has to get triggered. But then the bomb deactivating has to happen over here. And so, the sensor getting triggered by the tunnel and the bomb deactivating are two different events. Since they are at two different locations, there has to be some kind of signal to go from one end to the other. The signal, of course, cannot go faster than the speed of light. And so let's assume you use light as a signal, which is always a good upper limit. Then what you have is the train enters the tunnel, and here, let's just keep note of it. The sensor is triggered, which means it immediately sends out a signal that's going to the front of the train. But this train is moving quite fast, right? In this reference frame, it's going fairly, the way I have it now, it's going actually a good chunk of C, right? So while this is moving, this train is moving too. You can just, it is fine to just make this argument that it will work, but you can actually show it mathematically with some work, that the light will not be able to make it until the train reaches the front of the tunnel. And so what happens is, the sensor is triggered, but then the train reaches the front of the tunnel, and then the sensor reaches the wall. That last one maybe seems not so exciting. Now here's an interesting one. Now, in the train's reference frame, this is straightforward, right? Because then, boom, right? So step one is boom, right? Okay, but here's one for you. Let's assume this explosion is big enough to destroy the whole train, right? I told you that an event that happens in one reference frame happens in every reference frame. So, how can the sensor get triggered in this reference frame if the first thing that happens is the train blows up?
Order of events. You said order of events of relatives.
Right, but if this event happens first and blows up the whole train, the sensor's not going to get triggered. Not like usefully.
I just this the bomb.
So the bomb blows up and then the explosion doesn't reach the sensor.
Very good. The bomb explodes, but that explosion also takes time to move because everything takes time to move, and it can't go faster than C. So because of that, the explosion now is working its way down, but as it's working its way down, what's also moving?
The train.
The tunnel in this case,
tunnel.
right? Yeah. So the tunnel is still moving, so the tunnel will still hit the end, and then next you have the sensor is triggered, and then you have the sensor reaches the bomb really quite late. So notice I write out these events so you can see. You always have the bomb exploding before the signal reaches the bomb in all reference frames. But this order is what changes. Right? This order of the sensor versus boom. Right? This changes a different reference frame, but the sensor signal reaching the bomb always comes last. So like we mentioned before, some events have to stay in the same order, and some events switch order. And the fact that some events can switch order and some events have to be in the same order is what allows us to make these fun relativity paradoxes. We call them paradoxes, they're not really, of course, because they have answers, right? But I have to tell you, the answer is always the same. It has to do with simultaneity and usually some kind of